This is Shahid Rahman from Military Institute of Science and Technology, studying nuclear science and engineering. And in today's video, I will walk you through how to build a simple nuclear pistol. Then I will explain it to a fuel assembly. Then I will model a very basic nuclear reactor core design. And today the reactor model will be like a reactor, like rectangular in size, and the assembly as well with the rectangular in size. And then I will perform some very powerful neutronic simulation that you can perform as well. So from flux distribution to fission rate analysis, whether you are new to reactor physics or just exploring OpenMC, this can be a great place to start. So let's go. So this is where we will go to the OpenMC code, and this is where the generated file will be presented. So this is assembly. This is assembly. This is our assembly. This is spacer grid, and this individual is pencil. So first of all, we have to create this pencil first. You can see, and this is rectangular in size in OpenMC. We create this size with OpenMC.rect_lattice, and we place this pencil in individual lattice point as pencil universe. Okay, this lattice point can take only the universes. Okay, and center to center distance of lattice point to point distance is known as lattice pitch. Okay, the lattice has a center and lattice has a dimension as well. Lattice has a lower left and upper right as well. Okay, so first of all we have to create this pencil, then we will expand it into a assembly, then we will decorate a core. So for defining a reactor nuclear pencil, we have to define the material first. So material, for fuel materials we will use uranium dioxide, for cladding we will use zircaloy, and for moderator we will use like water. So I'm telling you, you can take the help of ChatGPT as well. So ask for ChatGPT. So go and ask for ChatGPT. Hey bro, just give me just type code for zircaloy. Okay. This is nonsense. So I'll copy this and paste it here. You see, binding material is done. So next step is for the boundaries. So for pencil, you see how the pencil look like. This pencil has three region and with two boundary. So in OpenMC we can create this kind of boundary with like R1 goes to OpenMC dot Z cylinder. This cylinder will be made with Z axis. The center will be in Z axis. Okay. Let's cylinder. Okay. You can also make a cylinder whose center will be in X axis. Then you will have to type like X cylinder, Y cylinder. Okay. Z cylinder, and as the shape is cylindrical, then this will have a radius, and let's say this is 0.48, and then another radius. We need this is R2, this is 5. So now we can define three regions, one for fuel, one for cladding, one for water. So let's say this is R1. Okay, good. So this is F cell. F cell is equal to. So how do you define a cell? We say OpenMC dot cell, and cell must be filled with a material, and let's say this is uranium oxide. You see, this is uranium oxide that you created for like as material. So we have to give it a region, the region in which the material will be presented. Okay, the region will be R1 negative. Why R1 negative? R1 means like R1 means this boundary. Okay, but negative R1 means inside this R1. So then we have to create a cell for cladding, the clad cell. So this is zircaloy, and region will be positive R1, and here's the logical end, and negative R2, and nothing and nothing. And you see, we are not giving this cell any height at the end of our like defining geometry. We'll like add this height. Okay. So clad cell is done. Then it's our work to define a cell for our moderator cell. So m cell goes to OpenMC dot cell. So the cell will be filled by water, right? This is water, and the region will be what? Positive R2. You are right. So the cells are prepared. Now we need a full universe. What universe does? See, this is I don't know what this is called in individual. I say this is liquid bottle. I don't know. Anyway, this is A, this is B, and combining them, this is C. So this is cell, but combining them, this is good night. So this is your universe. So universe means combining a bunch of cell. So F universe, how do we define this? OpenMC universe, and let's say cells. What will be the cells? F cell, clad cell, and M cell. Nothing else. Our full universe is done. Then what we have to do? We have to place this full universe into our assembly lattice. I already told you this kind of structure, lattice, this kind of like rectangular shape, and the rectangular shape where you can place your pencil is accessible from a pencil by rectangle lattice, and if you want to create something like this assembly, you will need like hexagonal lattice. Okay, this is also accessible from OpenMC. OpenMC has this kind of lattice as well. So what I'll so before that I will create a universe. The universe will contain water because the lattice contain a universe as its outer. Okay, if this is your assembly lattice, then outside of this assembly is assembly's outer, and this outer is actually the universe. That universe can't have any region. Okay. So OpenMC dot cell, and it is filled with water with no region. This is universe. And universe will have multiple cells like S, W, cell. Okay, this is your outer, and that will be used in your assembly lattice. So now define this lattice. So I already told you it's a rectangular lattice, so I will say rect lattice. The rect lattice won't have a name. You can give us a name. I don't need assembly must have the center, and I say here's 0 center. 0 by 0, and assembly. This is very time consuming. Oh god. No, no. Okay, this assembly has pitch, PTCH. So let's say pitch is, what is pitch? Pitch is center to center distance, or lattice point to lattice point distance, like center to center distance. But this I prefer, I will say this is 1.3598. this has to be larger than your pin cell diameter. Okay, 1.3598 comma 1.3598. okay, then this assembly has its pitch, this outer. I was planning to give its outer at the end, like what will be its outer, this universe will be its outer. Then it comes on assembly's lower left, that must give. Okay, lower left means this coordinate. Okay, so in x direction, what will be the distance from center to this end? Like 5 times the center to center distance, like, right, which is 1.3598. so 1.3598 times 5 is negative this value, negative 1.3598 times 5 is this position, and in y position this is same, right, negative 1.3598 times 5. So I will say negative 1.3598 times 5, same. And I will, and another is upper right. I didn't put any full universe, right? You can see any full universe here. So how do you do that? How do you put our full universe in each lattice point? We say universes. Let's say third, whatever. So I already told you I want 10 full universe in x direction. So I will multiply this by 10. This ensures that full universe is placed 10 times in x direction, and if you multiply this again by 10, this ensures that it has 10 full universe in x direction, and same row is like copy and paste it 10 times in y direction. So you get 10 full universe in x direction, then copy this 10 times in y direction. I have to place this assembly lattice into a cell. Okay, so let's say the assembly cell will be like cell OpenMC dot cell. Very easy, right? Very easy. OpenMC cell will equals to assembly, and I need to give it a region, like region equals to, and you can see the region has to be rectangular in size, right? So OpenMC has built-in a rectangular boundary. What is that? This is OpenMC dot model dot rectangular prism. Rectangular prism. So this is just a boundary, but when I say this is negative, that means Dyson negative OpenMC model rectangular prism, and what it has two things, width and height. So WEIGST, width bana raise width, and what will be its width? See, if center to center distance is 1.3598, then what will be the dimension in x direction? 10 times 1.3598, na? Yes. 1.3598 times 10, and it needs a height same, like same. Now it's a region, and it's now there is a bound like cell. That cell is consisting a assembly lattice. I need another cell that will consist like water. Okay, so what I have to do, we have to do assembly water cell OpenMC dot cell and fill by water, and region same region and that our assembly has, but opposite. Okay, so now you can now you have to now you need to create a assembly first. Dot universe universe itself as cell as water cell. So you can easily as so this is how this is our assembly, and if you wanna like plot color, if you wanna give it a color, like no, let go. So this is how our assembly look like. Now we know what we need to do. Let's say this is your core. Now each lattice point will consist what? Each lattice point will have assembly universe. Okay, and nothing else. So at the same way we'll create a core lattice. So how do you do that? As water cell 2 OpenMC dot cell, this is filled with water, and then as universe 1, so water uni 2. So this is like OpenMC dot universe, and the cells what will be the cells as water cell 2. Okay, the same way we'll create something like that. So this is copy করতে মন চাচ্ছে ভাই, let's say copy this and change this name with, you see this is now not a pencil, this is an assembly. I already told you that this is pencil, then the minimum value for pitch will be their diameter. So when we are like placing our assembly, then the minimum pitch will be the assembly dimension. Core pitch, then this is multiplied by 10, because this is height or width, you can say this is width of an assembly, and this is height of an assembly. Okay, so this is the minimum value. So let's say this should be 1.4598. So because we are not taking minimum value for our core pitch. So anyway, this is 2, this is it, then the lower left 2, 4, 5. So 1.4598 times 10 times 5. Why? This is a question from me. Okay, you better, whoever watching this video, should analyze why this line. Okay, this should be like assembly universe, as assembly universe, it should be here. And what this ensures that if this is a core, then there will be 10 assembly, and it will be repeated for 10 times in this direction. Okay, so this is your core lattice. So now, as we created a cell, that cell was consisting our assembly. The same way we'll create a cell that will contain or carry our core lattice. So let's say the name should be core cell. OpenMC dot cell field 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 with core lattice. Okay, and what will be its region? The region should be, this is core, and the region should be what? Inhibitors. If the pitch is 1.45 times 10, and there is 10 assembly in x direction and 10 assembly in y direction, then the core size should be like 1.4598 times 10 times 10, right? So region will be rectangular in size. So I will copy this and paste it here. Of course, negative, as you know well why I am giving it a negative sign. 1.4598, and this is also 1.4598 times 10 times 10 times 10. Okay, so this is our core, and I want water outside the core, so I will create again a water cell. So core water cell will be W post OpenMC dot cell filled with water, and the region should be same but opposite. So universe will be like OpenMC dot universe, and this is sound করতেছে cells, C cell and water cell. Now we will create another cell that is necessary, actually two cells, like cell 1, OpenMC dot cell, like fill with what, I don't know, fill with pure universe, fill this universe, and the region will be the same like this in this universe. Just see what I do. 1.5986, just make it 5, just make it 5. Now you can see this is your cell, and this is containing your universe, and there is another cell that I need. This is cell 1 and cell 2 with different dimension. You better analyze why I'm doing that, why these values are different. If I take our core like 200 centimeter in height, and then there will be like negative 100. Okay, then again, and negative OpenMC dot z plane, and the z naught value will be like positive 100. Okay, at the end, as you can see, as there is so many boundary, but I didn't give any boundary condition to any of the boundary. So now I'm gonna give boundary condition to this, the most outer boundary. So this is the most outer boundary in x and y direction. So I will say this is the boundary type, be like reflective. আমার ইচ্ছা OpenMC dot universe, and the universe will be cells, will have cells like what? cells like C1 and C2. After that you can watch your universe. This is your universe. So beautiful, right? মাথা নষ্ট করা সেই লাগতেছে. So anyway, you can give it pixels 1000. Okay, and also say color by material, material, material and colors. So uranium oxide should be like red, just my preference. I know some will say this is very bad choice on color. Okay, anyway, I don't care. I don't check people preferences. Okay, this should be blue, black, and zircali should be like blue. And then last but not least, what is that? This is your steel. Like, why? No, let it go. Let it take a beautiful color. Oh God, this is your reactor core. You see, such a beautiful core. Super. Like the blue here, you can see these are cladding materials. Okay, this is outside core water, and this is steel. Okay, so now for running simulation I have to give it some settings. I have to give it settings like settings is just OpenMC dot let's comment it. Let's make it a comment. Settings and settings. I should have a batches, like I want 100 batch. Settings should have inactive batches for which it will not carry any tally data. Let's say this is 10, and then settings dot settings dot particle. Okay, particles 10,000, let's say. Okay, let's say settings dot particle, there is source OpenMC dot independent source. So you are saying source. That's all. Now anyway, I didn't convert it into a XML sheet. So geometry is equals to OpenMC geometry unit, and then like geometry dot export to XML, and say settings dot export to XML. So if the XML settings is done, then we are ready to do simulation. I need some tally. What tally does? Tally statistical calculation. Okay. So tally does some statistical calculation in there. Tally is used to OpenMC dot tally, and let's say tally anyway I need 3 kind of data: heating local, flux, and like fission data, fission rate. So that's why I need a mesh. OpenMC dot mesh, regular mesh, regular. And the mesh should have, anyway, I have a mesh created, and I will mesh. So this is a mesh. Mesh has dimension, mesh is lower lift, mesh is upper right. Or lower lift, where did it come from? This is actually, if this is the core, then core, this is the core, then core low, this is your core that you can see from the cross section, and this is your lower left, this is your upper right. Okay, so this is there was assembly, 10 assembly, and assembly dimension was 1.4598 times 10. So this position is 1.4598 times 10 times 5, and this position is 1.4598 times 10 times 5. So this is 4, like this is 4, this is 4, and this is also 4. And I already told you that my fuel, like if this is your fuel, and also my core has this size of fuel, and only this size will do fission reaction. That's why the size I take the size is 200 centimeter, right? So the lower left will be in z direction, this will be like negative 100, and this will be like positive 100. Anyway, so this is your mesh filter that must be added, because with this mesh filter you will include this mesh in your tally dot filters. Of course there is an X, because you can add multiple filters in here. So this is your filters, and this is mesh filter. Go to add filters, and then what you have to do, you have to like tally dot scores, like what kind of data do you want. I want flux, because I want to show you flux, and heating local is for power calculation, like to show you power. My reactor core is generating in each position, and flux, and this is for fission. Okay, so anyway, this kind of data will be collected as my tally is defining a tally is done. And see dot, so now I will put this tally into tallies, like a bunch of tally creates this. Now I will create these tallies that will carry this tally data, and I will convert these tallies into XML file. If this is done, then you have to just type OpenMC.run. Simulation is going on. Let's see why it ends. taking too long. এত টাইম তো লাগার কথা না, কিছু পান করেছে maybe. Oh god, after all. So all the simulation data is collected in this file, so I have to access this file for further data manipulation. So I'll say space equals to OpenMC dot state point. So let's say state point dot 100. This 100 is your batch number. Okay, I'm saying that you can see you give 100 batch in your settings, and that is presented in here. Okay, so anyway, st file means statement point file. State point file is carrying your tally data, so you have to extract the tally data. Tally is to sp dot get tally name. What was your tally name? This was heating local. Okay. So this is frame. So this is working. This might take like 20 seconds more, maybe, I don't know, to do 25 seconds. File isn't that big. File isn't that big. It takes like 20 seconds. You see, there is 12 million data. Cause this was a reactor. You divided it 22,000 cell in X direction and 2,000 cell in Y direction. To 2,000 multiplied by 2,000 means 4 million. And each cell it scored 3 data: heating local, fission and flux. So 3 times 4 million means 12 million data is. So I don't know this 12 million data. I need in our first simulation, like I need like neutronic. In our first neutronic analysis, I need only the heating local data. So what I will do, heating local data is basically the power that my reactor generated, but as since I didn't specify any source strength, by default my OpenMC is calculating the whole process with source strength 1. That means my data is in unit of per source particle. So to get the actual power, we have to normalize the data. Okay, so in my further work I will show you how you can normalize. It's very easy. You can ask ChatGPT how do you do that. So anyway, power will be this is tally data. I am collecting a tally from another tally. In that case, I will use get slice, and in that case I have to say the scores. Score was heating tally, heating local, bro. Whenever heating local, this is done. So now this is a power tally, and we have to do like we wanna plot in X direction the position and in y direction the heating local value. Okay, relative heating local value means the heating local value will be divided by the maximum heating local value. Okay, but you can see we have 4 million heating local value. So how can we, and why how 4 million, 2000 data in here and 2000 data in here. So what I have to do is like, oh, my mesh size was 2000, 2001. That means it also calculated in z direction. So I wanna say in 2000 exposition, 2000 heating local data. So how do you convert this 4 million in 2000 data? How do you do that? You have to mean over z direction and y direction, as the convert after doing that, and the 4 million data will be converted to 2 million data. Okay. So how do you do that? First of all, you have to do like heating, suppose heating data equals to power dot mean, and then heating data reshape. We have to reshape this, reshape heating data reshaped. So you can see what you have to do. You have to reshape this, or what reshape we have to type dot reshape, and the size should be like 2000, 2001. So, and after doing that, we have to plan. We have to like suppose heating equals to like heating data reshape. We have to mean over this dot like numpy dot mean. Oh, okay. Anyway, let me do heating local reshape. Axis is equals to 1, 2 means 1 means y direction and 2 means z direction. Anyway, to perform this action, we have to import numpy as and p. We have to import numpy as and p, and also import matplotlib as plt, matplotlib dot pyplot as plt. matplotlib. Anyway, this will give you 2000 data actually, and after doing that you have to do like so you got 2000 data, and you need the position. So x position. So let's say you have to create this position, right? np dot line space, and reactors, if this is x direction, what is this end? This is 1.4598 times 10 times 5. So line space negative 1.4598 times 1.4598 times 10 times 5, comma. There should not be any negative sign. And as we have 2000 data for plotting in y direction, so we need 2000 data in x direction. That's why we are splitting this in 2000 section. Okay, this is the x position. So now we are ready to plot. Oh no, we are not ready to, we are willing to plot the relative power, right? So relative power should be like this heating np dot max value relative relative power times heating max. Okay, So now we are ready to plot, like plot plt dot figure, and then plt dot plot. So x direction, again I made the same mistake as before. So anyway, so this is your power looks like. The power your core is generating with 5% enrichment of uranium. So now in next neutronic analysis we will say the neutron flux, how the neutron flux look like. From the neutron flux it will be like you will learn where the most neutrons are present. Okay. The region where neutrons are present. Let's see the neutron flux in our eye. Okay. So I will say flux. I need the flux tally data. So from tally, I will say get slice, and the scores. What is the scores? And this was flux scores. So now I need to shape the flux data that I just collected from the tally. So I will say flux dot mean dot shape. What the shape should be? The shape should be like 2000 times 2000. Okay. And then I also need the fission, because I also want to see the fission region where the fissions are occurring. Okay. Fission, the fission is equals to tally dot get slice, and the score should be scores as like fission. So we got fission dot mean dot shape. So what the shape should be? The shape should be 2000 times 2000. Yes. So this is flux and fission, and they are ready to be shown. So fake ম্যাটপ্লটলিব এটা তো ইম্পোর্ট করা হয়েছে ডট ফিগ ডট subplot subplot 1 2 1 fig I am sure fig dot I am sure. Let's say this is figure 1 and figure 1. Let's say this is figure 2, and this is 2, and this is fission dot mean. So this is your result, and you can see every green line, like every green you are saying is the place of pencil, and every pencil is causing nuclear fission. So basically by doing this part is showing the region where fissions are occurring. You can see the most bright region is here. So that means most of the fissions are occurring in the center. You can also see most of the power also generated in the center, and you can see the flux also, maximum flux is also present in the center. That means the most of the power generation must be in the center, right? So this is neutronic analysis. In real life you basically change the different, and there are multiple type of assembly present in real life reactor. So you're by changing the enrichment in individual reactors assembly, you just balance, you try to make balance of neutron flux, you try to make flatten the neutron flux as much as possible. Like you want to see the green the blue light all over the reactor core, the blue light all over the reactor core, right? In real life the power should be all equal. You try to make sure that power is all equal all over the reactor core. Okay, in my next and last, I want to show you the neutron source particle. Like I like in settings I declared some particle, right? 10,000 particles are acting as a source. So I will show you the source and the direction where they are moving. Okay, where they were moving. So how do you do that? Let's see. We say plt.quiver. It's a very like short code. All the data that you need, we collect it from the statement file. So sp dot like source. I show your source like r. R is for the arrow. X and then sp dot source. So your source like also r. Source r. Oh, and this is right. You can see the more or less equal distribution all over the core, the neutron source. Okay, source neutron. And if you see, if you scale 200, like 200, then the value, these are actually, these directions are vector. Okay, like there was a source particle, source neutron that moved in this direction. Okay, this direction, this direction, this direction. So if you scale it up, then it becomes smaller. You can see, you can see it gets smaller. But if you like, if you make it like 1, just see the size of the vector. Okay, if you make it 10, the vector will become much longer. You can make it 6. See the size of the vector. So these are the size of the vector. Okay. So So that's all for today. There is so many other neutronic analysis like those related to depletion. Maybe in my next video I will show you how depletions are uh, uh, how depletions are done, like what kind of data do we analysis from doing depletion, and so many other things that is related to depletion, like the boron concentration, samarium concentration, and any nuclear materials that is used inside the core element that absorb neutrons. So in order to by doing depletion, we can see the uranium concentration over time, how its concentration is changing, oxygen concentration changing, like if oxygen absorbs neutron. Okay, so in my next video I might show you these things, and I was planning to upload a single video and doing all the neutronic analysis, like show you the 10 or 12 neutronic safety parameter in a single video, but I don't have that much time. But I hope inshallah next 2 or 3 video will cover this all out. Okay, so till then, stay safe. Allah Hafiz.